great, my great honor to introduce Phil. I've known Phil for about 4 or 5 years, something like that. Phil first approached us asking to present at the Fungus Fair. It didn't work out for the first year or two, but eventually he did a booth there and a talk at the Fungus Fair when I was the Fungus Fair chairperson. And then later on, a couple of years ago, he and I spoke together at an opening for his art show in San Francisco. And that's when I really got a sense of what he really does, which is absolutely remarkable. He is basically a pioneer in fungal engineering, using fungi to create shapes for, in his case, art and furniture. And other people have kind of taken this on. There's a company out east now that is using the same techniques for making packing material, using fungi, which are totally decomposable and totally a really fascinating way of using fungi. So I'm going to let Phil talk to you more about his background and his history, and without further ado, Phil Ross.
Let me destroy the place. Can you hear me? Did I just unplug this? It's okay?
I'll turn it up a little bit. Yeah, a little bit. Try that.
Hello, hello. Yeah, good. Everybody, top row.
A little more.
Top row. Good. Okay. Well, thank you all for showing up. And thank you especially to the Mycological Society for inviting me, to JR and Ken and all these other folks who I've known over a couple of decades now of association with this group. I used to be a member and then sort of floated through in various ways. It's interesting, you know, at the dinner before this, I was sitting across the table from Dan Campbell. Is that the name? And you know, we were talking about the local ecology and getting a sense of when the mushrooms are going to be growing, and this, you know, what is called terroir in the wine world. You know, like a sense of the earth as it's producing certain, you know, like as it comes to a certain fruition. And I think that mushroom collectors are acutely aware of these local conditions and to sense in the air or a combination of factors that are going to give rise to certain biological phenomena. So that's, I think, like, you don't find many civic, scientific groupings, you know, outside of academia where there is this, like a confederacy of spies, you know, people who bring a lot of information but aren't fully willing to share everything quite yet. So it makes for an interesting atmosphere. So I bring this up on the screen. For those of you who don't know mushrooms so much, this is a choice edible called chicken of the woods, which has somewhat like the taste and texture of chicken. And this is a particularly yummy nub of it. It's just this, you know, the first growth of this enormous part of this mushroom. And you can see here this kind of engulfing of this piece of the wood that it was growing out of. It was growing out of the side of this tree and started to assume the bark there, just kind of fully closing around it. And I think it's these kind of observations of just noticing the weirdness of how mushrooms grow in different conditions that give rise to a good sense of the organism. You know, we saw downstairs some amanitas, you know, which are considered to be one of the most poisonous mushrooms for, you know, causes a lot of toxic outcomes. And there they were on the table, and they were sun-bleached and looked like one had maybe grown from between a rock or something like that, or like it had some particular way of the environment in which it grew, which gave rise to this very particular shape. And if you're not familiar with the organism and the spectrum of possibilities of what it might express, it would be very difficult to identify that mushroom. It's not true to type, as we would say. So you just notice a lot of the weirdnesses and sort of like the outer wavelengths of the expression of the form when you do collect quite a bit, when you actually, you know, commit to going out into the woods and continuing to go out into the woods. The first type of mushroom forming that I did was very somewhat passive. When I started to collect hard mushrooms like this, these shelf mushrooms, which aren't very good to eat, are incredibly difficult to, impossible to eat, maybe, hard as a tree. I was collecting these for medicinal purposes, and so I went from looking down on the ground to looking up in the air, and it was a very different experience of hunting mushrooms. And I think that change of geometry changed how I thought about the growth of these forms. So usually mushroom hunters will go back to the same location, many times a year or at least once a year to kind of check in on what's happening, their spots, or to see what's growing. And so I would return to my spots looking for these things, and I would alter the trees that these mushrooms are growing on. So I would take a tree, alter its geometry in relationship to the sun and the earth, and then the following years I would come back to collect the artifacts along with the mushrooms that I was getting. So in this one here, this is very large. This is maybe 18 inches across. This is a Ganoderma, which again, like you'll see them anywhere that there are trees in the world. You'll find something like a cousin of this mushroom, and you can see there where I tilted it to this particular angle, and then the rim of the growth, kind of the outer perimeter there, started to alter. So it started to form all these little nublets, or whatever you call it, in this right angle geometry. And so it was just this kind of watching how things would grow, observing them in the wild, and starting to do stuff to them from just changes of basic geometries. This is the Ganoderma Lucidum, or a close cousin of it. This is on the East Coast, up in Maine, and growing out of a tree. And most of the action is actually happening inside a tree. I know a lot of the people here are very knowledgeable about mushroom biology, so I'll just try to be a little redundant for those who don't maybe know all this stuff. So this thing that's poking out of the side of the tree is the fruit of the organism. The thing that we normally eat as a mushroom is this just very temporary expression of a much larger body. And that body is usually underground or inside of something. Like it's an interior spatial exploration that fungi often encounter. Their world is often inside. And this is one of the brief periods where they go outside. So they kind of enter into the atmosphere in order to reproduce, so that their seeds, their spores, will then be transmitted and then actually enter into the airborne phase of the organism, in this case, where it will maybe fly off, go around the earth several times before it will then land and start to grow again vegetatively. So inside of this tree, there might be this organism that weighs several tons. So when I saw how these grew, this is kind of this ambition, was to grow something where you would be able to fuse together the edges of this growing fruit by setting up the way that an organism would grow. They would then kind of, at their tips, join together. So this was kind of the ideal that I initially set out for, was something that looked as if it had grown biologically. It was obviously from an organic origin, but also was something very much man-made and artificial, and looked like some mechanical type of artifact, or something that there was design involved with it. This again is like an image inside of a tree. So when that wood decomposing fungi, you can see that fruit there off to the right. And then that white stuff that's inside of the trees there, that is the body of the mushroom that is engulfing and decomposing the cellulose, and doing this through this slow catalytic type of reactions that are going on, breaking down the cellulose and transforming them into the body of the mushroom. So I would take a small piece of that tissue from the mushroom and bring it back to my studio, which I decked out into a homemade laboratory. And the critical piece of equipment here, sitting on this desktop, is this big air filter. And so you pressurize air to go through this, and it makes this very smooth, flowing, super clean air that's removed things down to 1 micron. And so this gets rid of most of the ambient living things that are in the environment. And so you can start to practice what's called pure culture, in where you take a piece of the organism that has not been exposed to the outside world, and you try to find this without any type of infection from any other type of organism, and then try to propagate that out as a pure culture. So you have to have a very clean space in order to do this. So in addition to having this big, massive air filter on my desk, this room is also positively pressurized. so that there was always clean air kind of in the room, so when you open the door or the opening to it, there was a clean flow out, so there was never a flow of dirty air inside. And I would clean the space from ceiling to floor almost every day for a number of years, using very high-tech equipment and, and techniques. You know, it's like I get asked a lot of questions about mushroom growing. It's very difficult. That's like all I can say. It's kind of like mushroom hunting, in that you have to really commit to it in order to get any better at it. So it doesn't happen if you just go out once a year or just try to grow mushrooms once a year or even once a month. It's something that you need to make into a practice. Nobody sets out to grow orchids as their first plant. That would be sort of silly. And you know, growing mushrooms, it's also like people just think like this is going to be an easy prospect, like growing a plant or maybe a fish or something like that. But there's just so many variables, and most of the process is invisible, so it's not intuitive. So coming back, so these were taking a little piece of tissue from those organisms I find in my laboratory. These are gelatin test tubes called slants, and then that little piece of tissue will start to grow, like a little kind of fuzzy mold onto that. And once it's taken to that gelatin, then you can start to increase its volume. And sort of like the way that you harden off plants by taking them from a very gentle, delicate environment and feeding them just the kind of baby food that they need and giving them environments that they need. You do a similar thing with the mushroom tissue, this very small piece, and you keep on amplifying it and giving it more solid food and more hardy conditions. And the tissue grows exponentially. So at first it's very small, and then it gets very big. So it's called a run sometimes, and I understand that now. So like by the end you're running to keep up with it. So this is growing then this culture which has been expanded onto sawdust. And here you can see the stuff that's below the deck. This is the body, the soma, this vegetative growing thing, which is woven together. And then above it are these fruit. So it's kind of ready to reproduce. So after I learned how to grow mushrooms well enough, then I set out to make some of the artifacts that I was interested in. And it wasn't like, you know, I was really waiting to go. I'm not showing you many of the failed attempts here. So this is growing, you know, the Ganodermas inside of that box, and it will just kind of, what it can't eat, it will engulf. So like if it doesn't have a way of breaking it down, it will assume another object. So I would start to form, you know, negative spaces by having them grow around stuff, and ultimately I was successful in making some of these strange fused objects, but it was, you know, a good lesson in practicing esoteric arts, because I made this remarkable thing. It had taken me like 5 years to achieve this object, and it looked like a dog's chew toy or something like that at the end of it. So I was like, look at the end of it, like all of my efforts, and it's just like, you know, disgusting to most people. So it's like, you know, unappreciative. So, you know, I'm an artist by training, so this is like a fascinating kind of condition to be in, of an aesthetic state where people can't even see what's going on, you know, or it's misinterpreted as the grotesque or the horrific, and what's like I thought like a technological achievement. So you know, it causes one to then reflect on this larger concept of, you know, what is pleasing to us, or how do we recognize what's true in the world, or any of these, you know, big questions in aesthetics. So I abandoned this first attempt at making this artifact, and then tended to go towards the more fantastical expressions of the fruit. When you deny them the proper amounts of gases, you know, they start to express themselves in very different forms. Here, there's still this kind of this fusion of these kinds. These are cultured from the same organisms, separated in space, and then allowed to rejoin together. Only recently, I found out. I don't know if any of you are familiar with L systems or P systems, but it's a way of expressing the growth of certain biological forms and geometric expressions that conform to specific logics. And I saw this book on P systems recently, and this is an expression of an exponential growth of a tetrahedral structure that has certain conformities, and the computer modeling looks exactly like this. If you happen to have a book on P systems. I just suggest checking this out. So, you never quite know what you're doing. And then they went from both, this command of the fruit and also thinking about the soma, this body, that part of the brick that was down below. I was doing this for many years. As I mentioned before, I was growing these for medicinal purposes during the beginning of the HIV crisis in the mid to late 80s. Ganoderma Lucidum was one of the few prescribed medicines that existed at the time. And at the pot clubs that used to exist in San Francisco, there was often a table of practitioners of traditional Chinese medicine. And so in addition to buying your pot, for terminally ill patients, you could get medical advice. And so this is where I learned about Ganoderma, and it's an interesting take on the human immune system. So this is very slow. I mean, I make, this presentation maybe seem so logical where these things were going, but it was mainly just like being persistent and observing. This was a rather large chunk object. It was about 4 feet tall, kind of formed like a bell, and made cast like a bell, so it was in a double hold container, so the inside is hollow. And these takes a long time to grow, so often I would make watercolors of what I imagined the forms would look like as I was waiting for them. And I'll show you what so this is what I imagined I was going to do, is to grow these two kind of pieces of an archway but missing a keystone. And then I would have the fruit grow together where the keystone would be by creating the environmental conditions right there to attract the fruit to that place. So this is the mold that I grew that the mushroom tissue was put inside of. This is it taking in form. And then for almost a year, these were placed inside of a black box. And there was just a shard of light coming down the middle that would train the fruit to grow towards that area. And again, you can see this rather horrific outcome of this thing. But I mean, it's so, again, like to me, this is like the most beautiful thing in the world because I understand its history and where it came from. And quite often in the grotesque, it's this idea of something that's removed from its place of origins, which makes it so alien to us, and unidentifiable, and then allows the mind to sort of place it anywhere or into other unknowns. But when you do know where something is coming from, it gives you a very different concept of how something appears. This is another kind of conjectural watercolor for this one that I was going to look very much like Edgerton, thank you, yes. The Edgerton milk splash, this kind of microsecond event that takes place, and this was my version of the splash, but going the opposite direction, where something was just so slow, you wouldn't observe it happening. It's like slow food, or something, really slow food. It takes you a year to eat it. And I'm gonna, at this point, I think this was somewhat linear up to now, and now I'm gonna become non-linear. This is a kind of a mold to show you like the type of forms that I cast the material inside of. This is these things can be uncast instantaneously, so they don't have to stay in the mold for any period of time, but they are just in there to take a shape. And then once they're taken out of there, then they can start to all fuse together, which takes place over a period between 3 days and 10 days to allow the mycelium to rebond. That chunk that you saw was a blank for a stool. This project in which I was growing some furniture about 2 years back at the workshop residence. So I set up a mini grow room there and wanted to produce locally grown organic furniture, if I could, from wood from the sawmills up in Sonoma, and then harvested wood from salvage wood from the East Bay. So we found some down trees of walnut. We worked with a master Japanese carpenter, Paul Disco, who helped with the design of this to figure out how to integrate things together structurally. And I think we grew something like 200 different pieces of furniture over a 1-month period in about 4 or 5 different models. So here you can see this is while they're still alive. There's that moment in Alien, when he's like peeping inside the egg. So it's just like, I felt like, what have I done? And this shows, once these have grown out and are fused together into a solid form, I dry them out. And so mostly that's just like by putting fans on them and a dehumidifier. So it just comes down to a certain humidity level. And then they go through a wood kiln, which takes it through a certain heat bell to kill off the organism, because you don't want these things coming back to life. And what happens if they come back to life? Is they eat your face off. That's what happens. No, it's like, yeah, no, I mean, they'll eat your house, unfortunately. So after 10 years, your house will be gone. So you want to keep the furniture in check. So this is showing this, kind of cured on the left, and then on the right, this is then sealed with shellac. And I wanted to follow through on this. Shellac is not local, but I wanted a biodegradable polymer, and so shellac can biodegrade rather easily. And so this is the kind of assembly. You can see here, there's these through carriage bolts to attach the hardwood legs onto the body. And this is one of the Yamanaka stools. This whole series is named after Shigeru Yamanaka, who created some of the prior art that exists in this realm back in the early 80s. So I dedicated these to him for making this freely available to everybody. This is the Yamanaka McQueen, based on the fashion designer by the same name who died just a few years back. There's a show of his at the Metropolitan Museum in New York, and this book called Savage Beauty, and the ways that he treated materials and an understanding of how treatment beyond the primitive of natural organisms was quite moving. And so this is the Yamanaka McQueen in its finished form with walnut legs, straight from Oakland. Walnut from Oakland. So this has a consistency somewhat like cork in terms of the give to it. We made the butt receiving area to be slightly more cushiony, so there would be the proper give in the right lumbar regions. These, probably had to go through 60 different molds to finally come to this. This is a mold that has 12 different parts, so it's kind of a complicated thing to put together. And of course, I really love when the organism expresses itself, again, into this kind of horror show of its skin, and really changing from one state to another. That to me seems like a quite a resonant form of beauty. So I was aware from observations and some casual experiments with the possibilities of what one might do beyond these smaller artistic proposals. So I set out to build a full building using mycelium blocks to do that. And back in 2009, I built the first architectural structure out of mycelium called Mycotextural alpha. So working with the Far West fungi, actually the place that Ken was talking about for the tour, we grew something like 600 bricks with 3 different types of bricks that would form together into a catenary archway, so a self-supporting arch. This is then in the makeshift drying room. And then this is a finished brick. So these were pretty crude. And I wanted the fruit to be growing off of them, which was a bad choice. It's kind of like, working with glass and shipping 600 pieces of glass somewhere. So these were put together with pretty traditional masonry skills. So each brick had to form next to the next brick. So this is where we discovered a lot of the very interesting qualities about the mushrooms of how they work with dynamic forces on them. So, the harder you hit them, the more that they resist. And so using electrical tools became very problematic for us, just because of the energy that was going into them wore down our blades very quickly, as opposed to using manual tools. This is a very ancient way of making architecture. Like if you look at Ur or any of the ancient cities in Iraq or Iran, they were built in the same way, just by utilizing a piece of string. You can start to create continuous vaults and almost any other type of complex human geometry that we might occupy. So here's Mycotextual alpha in its sort of finished form as a tea house. This is my wife, Monica, who is beginning to drink the tea house. So what we did as part of the stipulation when this was shown in Germany was going on this tour to three different institutions. And so I shipped this off with the understanding that they were not going to ship anything back, that the German people had to drink the structure. So it was like it's yours. So we would chip off all the fruit first, these little antlers growing off the side, and match them with some nice complementary herbs to help activate the Ganoderma Lucidum, so things high in vitamin C, and also some nice flavors because it's a pretty bitter taste. One of the very interesting things about my mushrooms, which I showed you earlier, that kind recognition, when they come in contact with one another, they recognize each other, and then they actually start to fuse together. And so you can see here 2 bricks, living bricks that were put in proximal contact. They were just put one on top of another for 24 hours, and then it forms a permanent bond between them as the mushrooms recognize each other and then grow together. Their cells actually binding to one another. And it does a natural form of infilling, so it will kind of finish its seam if you create the proper conditions. And this becomes the strongest part of the structure because it's pure mycelium. There's no kind of other objects are there. And so you can design this to be, again, like the toughest part of the organism. Here, this is a scanning electron microscope of the cells of the mushroom. And you can see this is as they're kind of becoming arbuscular. They're going up into the air and exploring space in this way, in this very kind of free-moving way. And you can start to see some of the interconnections where they fuse together. And then they will do this type of clamp connections where they make this very tight type of mechanical connection to one another. And eventually, their cell walls will fuse to one another. So they form right angles and other types of very regular geometries that do this, that also add to a lot of their strength. Here you can see a surface. This is a wood chip that has been fully encased by the mushroom cells, and you can see where they start to do this kind of infilling around each other. So there's this grid work of the cells, and then there's this extracellular matrix. There's this kind of things that the cells then exude to fill in this thing, and it becomes this type of sheet, this pure polymer. And in some of the testings that I've done over at Lawrence Berkeley Laboratories, we proved that these things behave the same as pretty much any other type of polymer. So the default condition of oyster mushroom is like an expanded polystyrene in terms of its behaviors as a polymer. This is without doing anything to it. This is just like your bag of mushrooms is EPS. So you can start to assemble then monolithic objects from discrete units. So this is a very different concept of how to assume form from other types of manufacture. Usually if you want to make a monolithic object, you have to take it into some other state and then allow it to cure or transform in that. It's not taking a liquid and allowing it to set like cement to cast this building or something like that. So in this case, then you can take smaller units and then they will fuse into that monolithic object.
Can you answer a question?
I think so, maybe.
Back up one. Could you back up one?
Sure.
That's a pretty big object, or it's like 6 or 7 feet tall.
That's about maybe 4.5 feet tall,
Oh, I see.
maybe 5 feet wide.
Where is it while they're fusing? What's happening? Where is the environment they're fusing in? It's in a humid place where they're not drying out.
A humid place where they're not drying out. Yes.
Is that proprietary information?
That's, I brought up that, Dan's discussion that, so much of this is understanding the environmental conditions that give rise to particular expressions of the phenotypic, like the phenotype of the organism. So, if, like my environment is not necessarily out there, mine is inside also. It's very much inside the laboratory or inside of a smaller environment. And so it's paying attention to the organism in that way too. So there's this you can create tons of different microenvironments and then look at how the mushroom is expressing itself in those different ways. And so most of this knowledge here Again, it's not through chemistry necessarily or biochemistry, but it's very much about the administration of environmental controls that gives rise to most of this knowledge.
Well, do you, just if you can answer, do you construct the whole thing and then let it go together, or do you do stack at a time, or?
These are actually 3 stacks, so there are 3 kind of triangular units, and then they're just balanced on one another. And this form was made to be interlocking. There's these kind of channels which allow you to use bamboo to set inside here to reinforce this type of structure. So with these are pretty simple brick geometries. You can start to create a lot of different types of expressions of spatial infilling. This is the latest version of these universal bricks. We're calling fungal polyominoes. And polyominoes are a 2-dimensional expression of how to tile a surface. Like there are certain ways that you might cover a surface with certain shapes infinitely, any type of surface. And then there are these extrusions then into 3 dimensions, so they're kind of like a 3-dimensional polyomino, which, very much like Tetris, you can start to lock these together into all different kinds of forms. So all of these have fused together from this language of about 5 or 6 different blocks. You can, it's almost infinite. So this is very different than something like 3D printing, in which you're, trying to adhere each piece in a topology. But this is more of a free-form topology, in that, it isn't assuming when things have to come together or in a specific order that they have to. And this is a particular expression of this, like a particular scale, but you can make these, they're scale independent, so these could go down to, these same units could be the size of several microns across and would be able to do the same thing of filling in space in any type of way. So I'm gonna hand something around. I've been working. I'm just again like I'm showing you the pretty dorky aspects of this stuff, and not really giving you so much of the philosophy that led to this. But I've formed a company to take advantage of this knowledge of this stuff. So you're the first people to hear this, actually. Special for the Mycological Society of San Francisco. So it's called MycoWorks. So we will be a Bay Area-based company to produce different types of composites made from fungus, using fungus as a core. This one that you see right here is a combination of fungus and bamboo. And I'm going to hand around a little piece of this, which you're welcome to check out. Fungaloo. It's a new world for me. To take advantage of this. So I'm not going to sell you this thing. I think a lot of you know some of the potential of what fungi can do, and the energetic requirements to do this are much less than conventional manufacturing, where you would have to add polymers to make assembled wood products, something like assembled wood board, or other types of areas where you're using lots of resin to hold together your pieces of wood. So in this case, there's no resin that's used. It's only the mycelium that's binding this together. So we've done life cycle analysis, kind of primary life cycle analysis, to figure out like how this compares to, say, like an IKEA composite. And this uses about 1/3 of the energy of their composites, with an initial guess towards that, with the added benefit that at the end of the life cycle of this object, you can chip it and then add it to your compost. With a lot of these types of composites that exist now with assembled board, they just go into holding stations. There's no real way for them to decompose, and so they're just kind of held forever, with the hopes that someday we'll be able to figure out how to break down resorcinol and other kind of polymers. So I'm imagining there's some questions or something like that. That's the end of my images. It's only halfway through this. I thought this was way too many images, but
Let me turn the lights on.
sure.
So you don't use anything to bind the mycelia to the...
In this case, it's actually using an animal glue. even if you were to use like a Gorilla Glue for this, it would still be using 5% of the other types of composite, other types of glues that you would be using for that. I mean, the mushrooms get really weird, and as some of you might already know, and the potential for these is quite vast. You will eventually be able to grow computers and batteries and many other very far out sounding types of technologies using fungi. The polymers that they create, again, like they're doing this at room temperature, these kind of transformations into these polymers, and there are things that can be seeded directly into the material. So it's a very different way than of thinking about material transformation.
By weight, about how much is fungi and how much is...
In this one, it's probably about 10% mycelium in this particular case. When you get up to much purer mycelium, then it starts to have all different kinds of behaviors. But you can think of it almost like a polyfoam. And so you can start to get material qualities that are very much like vinyl and other types of complex polymers. Yes?
How does this compare structurally to like a 2x4 or something like that in terms of the shear capacity or
When you put it into a composite like this, you can start to get to structural capabilities, but it has to really be in a composite form.
Okay. In this form, the mycelium is mostly used as the glue to hold it together. The real structure is coming from the bamboo.
No, it's a combination of the two. So the core is slightly corky and giving, and has some flex to it, and then the outsides definitely help with the shear and how you're binding it together.
So we appreciate your particular interest in the art of these structures. At the other end of the mundanity spectrum, what are the prospects for mushrooms to take the place of styrofoam in terms of shipping computers and all the other stuff that we get and we don't know what to do with?
Yes, absolutely. Yeah, we can do that. Again, like Ecovative has taken it up to do this, and at scale, it will be comparable to expanded polystyrene. I mean, you can make airplane wings, boats. It depends on how you're thinking about your objects and how you imagine them coming into being. I mean, it's a very different. I mean, there's a lot of transformations that are happening in material production. Back in the industrial era, there was the machine. How do we say it? Like the machines used to be inside the buildings. They were so big that they had to be bound to an architecture. And then with the creation of the locomotive, the machine left the building. It sort of entered out into the garden of the world. The Machine in the Garden is this book on this very subject of thinking about the transformation of our landscape by these machines, leaving buildings. Now they're so familiar, we are barely aware of them. And so in this case, like the biological production has left the building. So a lot of ways, like making materials can now happen in the field. I mean, at the place where you're harvesting your materials can also be the place of production, because that's where the materials are located. So you don't have to bring that stuff to the building. You can go for the production. Now the machine will actually do that on site, or that possibility exists. And it just it depends on how you think about what you need in the world. I mean, the problem with this is it might be too cheap. So making objects might just become so ubiquitous and low energy that how we think of the durability of things might go through certain transformations. I look forward to the day that I'm just going to be able to throw all this stuff out of my car window, and just be like, well, it's just recycling, and just get it back to the earth, or something like that.
What's the lifespan of these?
The lifespan?
Yeah.
If you treat it, it should last for several decades. It's like a softwood, so if you kind of make sure that bugs aren't going to eat it, or that other molds aren't going to eat it, and you're kind of putting some seal on it, then it should be going on. I have samples that I grew almost 20 years ago without the state of the art that I'm practicing now, and they're still around. They're not great, but they still exist. Yes.
How flammable is it? How flammable is it?
It's actually fire retardant, because part of what the fungi are doing to transform that cellulose is they're oxidizing it, and so they're doing it in a very, very precise way. So they're trying to take it available, like all that's there for them to eat through that room temperature burning. So when you do have a flame hit it, there aren't so many places for it to actually catch. And it actually has to get to pyrolysis and gasification before it will combust. So it will smoke, it'll char, but it won't catch fire for 10 or 15 minutes on an open flame. Yes?
You mentioned that it forms in a room temperature. How long does it take to, let's say, form that sample?
This one probably was about a week.
A week?
Yeah. And then, whatever you're going to do with drying and all that will add time to it too. I'll keep on going across the room here. Yes?
Is the mycelium always Ganoderma?
I've been working mostly with Ganoderma, but I've worked with many other polypores as well. And the qualities of the mycelium are also very dependent on the host organism. Yes.
So have you measured or tested, run the gamut of mechanical property tests on it and accelerated lifespan and cyclicality?
Yes.
How does it compare with conventional materials?
It actually, sometimes when it weatherizes, it gets more durable. And again, like you can compare it to other assembled wood boards. But it also, you have to amend it with other certain chemicals to make sure that it's not going to break down, or especially with insects.
What do you say, it's softwood?
I think that softwood, but it's also like thinking about composites is probably a better idea. And again, definitely like things that are going to have something that's going to be fibrous with some type of density or durability mixed in with these softer cells inside of it. So you can, it doesn't have a specific given, and you can design it very much to.
Have you done other shape factors besides velocity?
Yes. I'm sorry, I can't give away everything quite yet, but we will be publishing. We're going to be publishing in the Journal of Composites, I think in San Diego this October, with much more of these findings.
So you were saying that using high-speed tools didn't work very well, like wore down your saw.
Yes.
So with these blocks, then, once you've got that shape, that's it, right? Or can you cut it?
You can form it. I mean, you can machine it. There's lots of different ways you can. A great thing about it is that you can form most of it in the mold. So if you understand how it's going to dry and the parameters of how it's going to dry, you can design the mold so that it will conform to
So
certain
you don't
shapes.
have to.
You have to do minimal machining afterwards. So I think with these ones we do just like a quick pass through, a sanding planer to just make sure that the laminates are going to stick onto them properly with a good surface. But there's very little post machining.
Are you sharing this with the world, or have you applied for any patents?
I have applied for a patent.
You have?
Yes, so there's a patent pending on the process around this and having to do with particular densities and ways that those are achieved in the organism. But I would also just say that, so much of this is just proprietary knowledge and is not necessarily anything that goes into that patent. But again, it's just like an understanding of the organism. Yeah, Ken.
So, when is Microworks having an IPO?
I hope never.
Oh.
We're going to
So
make
are you
profits.
You're doing what?
I'm sorry.
What would you say?
We're going to make profits. I think that's it's a different prospect
Yeah.
for how to run a business. And
So no Indiegogos? And
no.
Okay. You already have back?
A lot of interested customers.
Oh, okay.
How's the density compared to other wood?
Has the density?
Yeah, does it float better than teak or balsa wood or?
These kind of questions. This is like it's very much like how would you define plastic? So yeah, it can become an expanded polystyrene. It can become a hard ABS plastic. It can be almost anything in between those, depending on how you thought about how you want that polymer to take shape. So you can grow this onto very dense, fine particle materials and end up with a very dense, tough material. And then you can actually have that joined together with something that's really light and fluffy, and it will still be a monolithic material, even though it's a hybrid composite. And so you can start to design the material depending on what you want it to be like, rather than just what you're given. And so in this way, like thinking about the material combinations, the ways that it takes form, and also just like some basic material science of like where you do need those densities or where you need open pockets give rise to that. So, you know, yeah, you could have this as tough as you want it, but you could also have it as soft as you want it, depending on how you design it. Yes, up in the on the rafters
Well,
there.
thank you very much. This is one of the most exciting mycologically related topics.
Thank you.
I was wondering if you found other ways to inhibit the mycelium growth without using drying or heating.
The basic ways you kill anything, you know, I mean, you can use radiation, chemicals, deep freezes, so I mean, they're all good. Like it just depends on what you want to get. From the, you know, you can do salt. I mean, just like a really old school way of killing stuff and keeping it cured. Salt baths or lye baths are also really excellent ways to do that, or just even cutting off the oxygen. You know, you can put things into a vacuum, and that also will rupture most of the cells. But the reason with heat is I want to be 100% sure that this thing is dead. Because, you know, if one of these chairs is still, has just a few cells in it that are alive, there's, say, a catastrophic flood in your house, and then your chair has infected the rest of your house with dry rot, you know, so kind of have this mini time bomb ready to go. So I'm using, you know, I think like any good science fiction movie, like you go to the flamethrower when you really need to kill the life forms. So I was like, we'll use heat to bring it down. Yes.
Your molds look like they were wood, and I wondered if you have trouble getting the form out of the wood. I mean, in other words, does mycelia grow into the wood, or how do you get it out of the mold?
Yeah, mycelia will grow into anything. I've had them grow into cement floors. I mean, it's like I will leave stuff there, and it's like bonded to the cement. I mean, and that's because they're growing into the micro fissures of the floor, not that they're, you know, necessarily digesting anything. So in the case of the wooden box, there's a plastic liner inside of that. They would totally grow into that wood if I left it there overnight, and it would be, you know, they would eat the paint and everything. They're good eaters.
So in this case, you have it covered with bamboo. Can
Yes.
you finish the surface of it without bamboo? Is it?
Yeah, absolutely. And again, like it can go from something very fluffy and white to this very strange kind of beetle shell type of thing, and with all sorts of colors in between. So you can make it look like a very conventional, you know, like a plaster or something like that if you want to. It's been hard for me to make things so, you know, normal looking as this. Like this is definitely not my, you know, my given art aesthetic. Yeah.
I can imagine that they would make very good insulation as well.
They're an awesome insulator, yes. And the same way that you can design this so that there are air pockets where you want them. And so you can make heat transmission, again, like very clear how you want to do that. And also you can add a lot of amendments into these things. So you can put in things like perlite or even sand if you want to give weight to your material, but other things that are also going to increase its insulation capabilities.
Do they not get mold in them if they get wet?
If you treat them properly, they will not. And so this is part of it. You do have to put antifungals or, again, like salt or lye or something else that's going to inhibit that type of growth. That's maybe enough questions. I have some postcards here, so at the end of the meeting, please feel free to come and grab one or two of them. MicroWorks does not yet have a website up, but we will by April 4th or so. That is our sort of launch of being official. And so the website will have a lot of information about some of the material things that we've published already, and also some of the capabilities that the company is ready to handle.
So the other company that's sort of working on stuff like this is Ecovative Designs in New York State.
Yes.
And are there other people working on this? And how do you see yourself compared to Ecovative Designs?
I don't.
They're more functional. They're going for like a commercial applications like insulation,
Sure.
functional things.
Yes.
You're more going at.
I think that they're going to be going for housing materials as well. They sponsored a project at PS1 in New New York for the summer, in which they are growing the first fungus architecture made from fungal bricks. Is the claim. So I think that there's a lot of interest. For those who are working with this, it's kind of apparent what these can do. You can grow 4 times the amount of material in a given hectare with these materials than wood, with using bamboo and fungus. So, and again, like using 1/3 of the energy, the possibilities are gigantic. So I'm assuming that there's going to be a big crowd, actually, and that myself and Ecobit were maybe just the first to have showed up at the party, but that there's going to be a lot more people coming. And it's more than I think either of us would be able to handle with the possibilities involved with this. So I'm assuming masses as the future of this. Obama, like he had a speech about 4 or 5 months back or something, and he was talking about carbon sequestration and this I think $1 trillion goal that in 10 years we were going to be able to do X amount of tons of carbon. And when he gave that announcement, like, I quickly did the math. I was like, I know how much carbon sequestration you can achieve with this, and I was like, we can do it, at 5% of the cost in 5 years. I was like, it's done and done. So it's like, okay, come on, give us another challenge. And this is the way that we will do that. And it's not like technology that we have to wait for, or something that's with enough bootstrapping it's going to occur. The technology requires something advanced beer making and other forms of industrial production to make materials like this on scale. So every country on the planet has those technologies already. I mean, everywhere I've been has beer. They don't even have a civic government, they have beer. So I know that infrastructure already exists, and if the source material is bio-waste, this is also something that we're swimming in, and is a giant contributor to carbon, the carbon cycles on the planet.
I mean, do you see a future where, like, our refrigerators are going to be made out of this stuff, or how about cars?
Yes. Yeah.
Really?
Yeah, absolutely. Ford, you're asking about other players. So Ford, 2 years ago, took about 15 patents on mushroom materials for their cars, with lots of very interesting advanced nanoparticles invested in them to make them into sensors, and also to be reactive in lots of ways. So I think a lot of people are aware of this potential, and we're just, and we're not quite there yet, but I think soon enough we will be. Yes.
To give you an example, she was talking about cars. I was just at the Harris Automobile Museum yesterday in Reno. Many of the early automobile frames were made of wood.
Yes, yeah, and
The
soybean plastics, yeah. No, I mean, yeah, they do great on impact. I've crushed many a steel with fungus, and they do very well in high impact situations. I would rather be in a car made of fungus than metal. From what I've seen.
Well, thank you very much.
Sure.
Thank you.